Washing soda crystals contain about 1/3 sodium carbonate and 2/3 water of crystallization. In this form, they don't cake and they dissolve easily. If heated, they lose the water and become 100% sodium carbonate. This is the sodium carbonate, or soda ash as it's known, which is the raw material of industry. Soda ash comes from salt, sodium chloride, and limestone, calcium carbonate. The salt is in the form of brine, but quite a few reactions are needed before we can change chemical partners and obtain sodium carbonate. These reactions are known collectively as the Solvay ammonia soda process, first operated successfully by the Belgian Ernest Solvay in 1863. The main reaction takes place in Solvay Towers. The brine must be ammoniated. Ammonia is an essential intermediary. The brine is run into the top of an ammonia absorption tower and cascaded down it, while ammonia bubbles its way up from the bottom. Meanwhile, the calcium carbonate is split up in kilns by burning limestone with coke to give carbon dioxide and quicklime. All is now ready for the Solvay Towers. There may be dozens of these, worked in groups of towers which are interchangeable. All the towers contain a series of baffle plates. All have inlets at the bottom for carbon dioxide gas from the kilns. They have water cooling boxes to take away the considerable heat generated by the combination of carbon dioxide and ammonia. Cooled ammoniated brine from the absorbers is pumped into the top of the first group of towers. It cascades down over the plates, meeting the carbon dioxide blown up from the bottom under pressure. The ammoniated brine contains sodium chloride, water, and ammonia. The water and ammonia combine with the carbon dioxide to form what we call for simplicity ammonium carbonate. This, the first reaction in the towers, is monocarbonation. The salt does not yet react to any extent. The carbonated and ammoniated brine is pumped to the top of the second set of towers. Again, it cascades down over the plates, meeting more carbon dioxide gas blown up from the bottom. The ammonium carbonate in the brine reacts with the additional carbon dioxide in the water present to form ammonium bicarbonate. This is the second reaction, bicarbonation. It all happens at the top of the tower. As fast as ammonium bicarbonate is formed, it reacts with the sodium chloride in the brine to form sodium bicarbonate. This sodium bicarbonate becomes more and more insoluble on cooling, so once the bicarbonated ammoniated brine reaches the cooling zone, crystal growth is rapid. By the time the liquor reaches the bottom of the tower, it consists of a suspension of coarse crystals of sodium bicarbonate in a solution of ammonium chloride. The reactions can be illustrated with laboratory apparatus, using twin glass columns to represent Solvay Towers. Ammoniated brine is poured into the top of the first column and allowed to trickle down it. Carbon dioxide gas is blown in at the base. Blown up the column, it meets the ammoniated brine. Carbonation takes place with the formation of ammonium carbonates. Condensers are fitted corresponding to the cooling boxes. The solution at the bottom is mainly ammonium carbonate and sodium chloride. The solution is transferred to the top of the second column. As it trickles down the second column, ammonium bicarbonate is formed. This reacts with the sodium chloride to form sodium bicarbonate. The cooler the final liquor, the more sodium bicarbonate will be precipitated. It forms a suspension in the ammonium chloride mother liquor. When the suspension leaves the group of making towers, the ammonium chloride and sodium bicarbonate are separated by a rotary filter. The sodium bicarbonate passes from the filter into a rotary calciner. There it is decomposed by heat, giving up carbon dioxide and water, leaving the sodium carbonate that we require. This, then, is the essence of the ammonia soda process. As shown, however, the process will be quite impracticable, as it's not possible to sell more than a 50th of the ammonium chloride produced. So ammonia is recovered from the ammonium chloride solution. The quicklime from the kilns is mixed with excess water to make a suspension of slaked lime. This is mixed with preheated ammonium chloride solution and distilled to liberate ammonia, leaving behind a solution of calcium chloride. The ammonia distilled off is cooled and used to ammoniate further quantities of fresh brine. Another economy is to recover the carbon dioxide from the calciner and feed it back to the Solvay Towers. All the internal cycles and reactions are neatly dovetailed, and the only surplus byproduct is a weak solution of calcium chloride. Some solid calcium chloride is recovered by evaporation and sold for refrigeration, to the building trades, and for making other chemicals. The rest is disposed of and joins the natural drainage of the district. This one works in Cheshire can produce over 2,000 tons of sodium carbonate a day. Every single ton turned out needs 30 tons of water and 3 tons of solid raw materials. Coal for the boilers and calciners. Coal to generate electricity and drive the machinery. Coke for the lime kilns. Limestone from the division's Derbyshire quarries. 10 of limestone to 1 of coke. 250 tons an hour pass up the giant conveyor to the lime kilns. The carbon dioxide evolved there will be used to carbonate the ammoniated brine in the Solvay Towers. Left over is the residual quicklime. This is slaked with water in rotary dissolvers to produce milk of lime. This will be used later to recover ammonia from the ammonium chloride mother liquor. Meanwhile, in a building taller than Nelson's Column, brine from the rock salt strata hundreds of feet below the Cheshire Plain is saturated with ammonia. Inside the absorption towers, the brine cascades down, absorbing ammonia bubbled up from below. The ammoniated brine goes onto the Solvay Towers, more huge, tall columns several stories high. The eye sees little: pipes, columns, valves. The ear hears little, but inside the towers there is surging activity. Down pours the brine from plate to plate. Up, fighting against the current, comes the carbon dioxide. Monocarbonation, bicarbonation, precipitation. Such is the pressure of gas in the towers that the suspension is forced up into this trough some 30 feet up from the ground floor. Sodium bicarbonate precipitated in ammonium chloride solution. Onto the vacuum filters, large rotating drums covered with blankets. The ammonium chloride solution is sucked through continuously, while the bicarbonate crystals left on the outside are scraped off. They pass on to the calciners. Here the bicarbonate is converted to normal carbonate. The hot sodium carbonate passes along long cooling conveyors to the silos and packing sheds. The product from the calciners is light sodium carbonate. The type used in most industries by the makers of fine and industrial chemicals, by wool scourers and laundries, for dyes, for water softening, for making soap powders, and paper. One of the raw materials of paper is esparto grass, a tough resilient grass grown chiefly in North Africa. After vacuum cleaning, it goes into digesters, where it is pressure cooked in caustic soda solution. Caustic soda is made on the premises from sodium carbonate. It dissolves all non-fibrous materials and reduces the grass to pulp. The pulp is washed and partially bleached with calcium hypochlorite liquor. It is passed along shallow channels where any remaining heavy impurities like sand and grit fall to the bottom. Then more screening, more washing, more bleaching, till at last paper making can begin. The esparto pulp is put into beta flow mixers and agitated. Depending on the type of paper required, more or less wood pulp is added. Both types of pulp are thoroughly mixed in 95% water. Other ingredients are added: resin, size, starch, dyes, completing the recipe for the particular batch. The mix is refined, screened and diluted, and then launched onto a continuous wire cloth. As the wire carries it forward, the water drains out, leaving a web of interlaced cellulose fibers. The fiber sheet passes under a dandy roll, which applies the watermark. When the pulp is strong enough to support its own weight, it leaves the wire cloth. It is now paper. After drying, it passes over calendar stacks, which gives it its glazed finish. To consider the part played by the soda ash, we must go back to the digesters. Out of these, besides the pulp, comes spent caustic soda liquor, containing many impurities. To make the process economic, the caustic soda must be recovered. First, it is thickened in multiple effect evaporators, then pumped into a rotary furnace. In this, the organic constituents are burnt off, liberating carbon dioxide. The sodium compounds are converted to sodium carbonate. This, plus a small amount of unburnt carbon which settles out, is placed in causticizers of 10,000 gallon capacity. It is supplemented by 20% light soda ash, fresh from the factory. To this mixture of fresh and recovered sodium carbonate, quicklime is added. Quicklime and sodium carbonate, when mixed together, produce calcium carbonate and caustic soda, the lime soda process. After causticizing, the caustic liquor is filtered out of the chalk sludge. It is stored until it's needed again in the digesters.